Of today's lecture will enable you to understand the electrophilic aromatic substitution reactions of benzene, including nitration, sulfonation, and halogenation, and we will study ortho-para and meta-directing groups. Students, benzene undergo electrophilic aromatic substitution reactions. Means that on the aromatic ring, electrophiles are substituted. Means hydrogen can be replaced by an electrophile. But what are the conditions that are necessary? As you know that pi electrons of benzene are highly stabilized due to resonance. They are not readily available for the electrophilic attack like electrons of alkenes. Now you know that alkenes have a pi bond. It acts as a nucleophile and attack on the electrophile. Benzene also have such double bonds, but those pi electrons are not readily available to attack the electrophilic regions. They do not assist in the attack of a weak electrophiles. So students, if we are going to bring weak electrophiles to benzene for a chemical reaction, it is not going to react with the weak electrophiles. Hence, more powerful or strong electrophiles are required for such attack to penetrate and break the continuous sheet of electrons in the benzene. Students, let us look at the general pattern of substitution. The general pattern of chemical reactivity of benzene towards electrophiles is shown as follows. As we have already discussed that in benzene, substitution is preferred over addition in order to preserve the stable aromatic character of the benzene. Now students, this is a benzene ring acting as a nucleophile. When we are going to react it with a very strong electrophile, then this pi bond is going to make a bond with this electrophile. It can be any electrophile. Now since this carbon is going to make a bond, the valency of the second carbon is not satisfied, so it is getting a positive charge. Now students, in the presence of any base, what is going to happen? That instead of attacking over here and making a bond and satisfying the valency of this carbon, what happens? That benzene prefers to regain its aromatic character. This base abstracts a proton, and the bond between carbon and hydrogen is shifted in the benzene ring, making a double bond again. In this way, the hydrogen which was present over here in the benzene ring is substituted by an electrophile, and the aromatic character of benzene is again conserved. So this is the general pattern of substitution for electrophilic substitution reaction. Students, as I have already mentioned that electrophile should be a strong one in order to react with benzene. Substitution of halogen in benzene requires iron or the corresponding ferric halide, means iron with any halogen atom as a catalyst. It reacts with halogen molecule to produce a powerful electrophile. Now students, you can see the formation of a strong electrophile. Iron is going to react with halogen to give ferric halide. This ferric halide further reacts with halogen molecule in order to give tetrahaloferrate ion 3 along with a halogenonium ion. You can see X positive. Students, the second step can be written as follows. Now this is ferric halide FeX3. When it is going to react with another molecule of halogen, what is going to happen? As you know that this is a Lewis acid. Why? It is not having a complete octet, 2, 4 and 6. So it can easily accept a pair of electrons. So this bond between the halogen is going to be broken down. This is going to be shifted and make a bond with iron FeX, as you can see over here, the black X atom. Now students, since this is a complete headed arrow showing a complete transfer of this pair of electron, the other X atom is deprived of the pair of electron. You can see it is carrying a positive charge. Now students, why FeX4 is carrying a negative charge? Do not mix this concept with NH4. Because in NH3 what happens, that nitrogen in the center it gives its pair of electron to hydrogen to make NH4 and carries a positive charge. Why? Because its electronic density is being shared, but over here iron is gaining electrons. The electrons over here are going to be excess than its own electronic density. Therefore, it is having a negative charge. Students, in the first step, when a strong electrophile is generated, the second step is attack of the electrophile at the pi bond. The halogenation ion thus produce attack as a powerful electrophile on the electrons of the benzene ring. Now you can see that the benzene ring is going to make a bond with this strong electrophile, and this is a slow step. Now you can see benzenonium ion is produced. Benzene containing a positive charge is called benzenonium ion because over here this carbon is deficient in its valency. The X atom is added over here because this complete pi bond is making a bond with this X atom. Now students, in the second step, FeX4 negative, which was generated in the first step, is going to abstract this proton, just as the step which we have discussed in the general pattern. The base abstract a proton. Why? So that the benzene can regain its aromatic character. The bond between carbon and hydrogen is going to shift inside and make a bond, a pi bond over here, retaining or conserving the aromaticity of the benzene ring. Now FeX4 negative is going to abstract this proton. One H and X is going to make HX, and FeX3 is again going to convert into a neutral molecule. In this way, electrophilic aromatic substitution takes place. Students, the first example of electrophilic aromatic substitution of benzene is nitration of benzene. The introduction of NO2 group to benzene by substituting hydrogen means in this case we are going to replace hydrogen with NO2 group. Now the benzene ring, when it is substituted with NO2, this process is called nitration. What are the chemical reagents? You can see benzene, when it is reacted with nitric acid in the presence of sulfuric acid and heat, it gives nitrobenzene along with water. Students, as electrophilic aromatic substitution occurs in two steps. The first step is the generation of strong electrophile. So let us see how we generate a strong electrophile in nitration of benzene. Now students, HNO3 nitric acid is going to react with sulfuric acid at 50 degrees Celsius to give you nitronium ion, NO2 positive, along with bisulfate ion and water. Now this NO2 carrying a positive charge is the strong electrophile. Benzene is going to attack on this strong electrophile. It is going to make a bond with NO2 over here. The valency of this carbon is not satisfied, therefore it is getting a positive charge. In the second step, this bisulfate ion acting as a base is going to abstract this proton and shift this bond between carbon and hydrogen into the ring and restoring its nucleophilic character. In this way, H2SO4 is again regenerated. Students, the second electrophilic aromatic substitution reaction that we have to study is sulfonation of benzene. The introduction of sulfonic acid group in benzene by substituting hydrogen of the benzene ring is called sulfonation. When benzene is heated with fuming sulfuric acid or concentrated sulfuric acid, it yields benzene sulfonic acid. Fuming H2SO4 has free sulfur trioxide SO3, which is electron deficient, so it acts as an electrophile and causes the substitution. Now students, here is a one-step reaction. When benzene is reacted with concentrated sulfuric acid or fuming H2SO4, and it is going to be heated, giving you benzene sulfonic acid along with water. Students, the fuming sulfuric acid have free sulfur trioxide, which is electron deficient, as we have discussed. So this sulfuric acid, when it is heated at 80 degrees Celsius, it gives benzene sulfonic acid, or when it is reacted with sulfur trioxide at 25 degrees Celsius, it gives benzene sulfonic acid. Students, let us discuss in detail the mechanism of sulfonation. When sulfuric acid alone is used, the actual electrophile is SO3. 2 moles of sulfuric acid are going to react with each other, yielding sulfur trioxide as a strong electrophile, along with bisulfate ion and hydronium ion. Now SO3 is a strong electrophile. You can see the positive charge on sulfur atom. Now this benzene pi bond is going to attack on the sulfur, just like this. Now you can see when a bond is formed between carbon and sulfur, the pi bond between sulfur and oxygen is going to be broken down and shift on oxygen as a negative charge. Again, the valency of this carbon is not satisfied, therefore it is getting a positive charge. In the second step, the bisulfate ion is going to abstract this proton in order to regain the aromatic character of benzene. This bond between carbon and hydrogen is going to shift inside, making a pi bond, restoring the aromatic character of benzene and giving H2SO4. Now students, as you can see that hydronium ion was also generated in the first step. Now it is going to transfer a proton over here. The negative charge is going to carry a proton from H3O positive and is going to give you benzene sulfonic acid along with water, H2O. Students, the third reaction is halogenation. The introduction of halogen in benzene by substituting hydrogen of benzene ring is called halogenation. Now you can see Br2 in the presence of FeBr3 or simple iron. It is converted into bromobenzene along with HBr. Similarly, if we are using chlorine in the presence of ferric chloride, it will give chlorobenzene along with HCl. Students, let us look into the mechanism of halogenation of benzene. Again, these are the 2 steps that we have already discussed. Now, any halogen is going to react with iron halide. You can see FeX3. It is going to give you a strong electrophile, a halogenonium ion, along with FeX4 negative. For example, if we are taking Cl2 in place of X2, reacting with FeCl3, it will give Cl positive along with FeCl4 negative. Now, since we have generated a strong electrophile, in the second step, benzene is going to attack on this strong electrophile, making a bond. Now, FeCl4 negative is going to act as a base and abstract this proton, shifting this bond into the benzene ring, restoring its aromatic character and give you chlorobenzene. Now the hydrogen of benzene is substituted with chlorine. Now in the second step, what is going to happen that FeCl4 negative after abstracting this proton is converted into FeCl3. Now one of the chlorine atom is attached to hydrogen giving HCl. Students, when alkyl benzenes are treated with chlorine or bromine in the presence of sunlight, only the alkyl groups are substituted. Now you can see this is an alkylated benzene having CH3. In the presence of chlorine in sunlight, the side chain is halogenated, as you can see, CH2Cl. Now one of the H is going to make a bond with Cl giving HCl and the other Cl is attached over here. Similarly, when benzyl chloride is further reacted with Cl2 in the presence of sunlight, another HCl molecule is liberated, H and Cl, and the second Cl over here you can see now it is Cl2. Now this is called benzyl chloride. Benzyl chloride upon further halogenation gives you benzo trichloride liberating one more HCl molecule, now giving you CCl3. So one after another, one chlorine atom is being added and hydrogen being removed giving HCl. Students, one of the most important electrophilic aromatic substitution reaction is Friedel-Crafts alkylation. The introduction of an alkyl group in benzene ring in the presence of alkyl halide and a catalyst like AlCl3 is called Friedel-Crafts alkylation, or simple you can say alkylation. Now students, one-step reaction is that benzene is going to react with alkyl halide R and X. This can be chlorine or bromine in the presence of a Lewis acid like AlCl3 or AlBr3, giving you alkyl benzene. This R can be methyl, ethyl, propyl, whatsoever, along with hydrogen halide. So this is a one-step reaction of Friedel-Crafts alkylation. Students, let us study the mechanism of Friedel-Crafts alkylation. Now this is a alkyl halide. First of all, it is going to generate a strong electrophile, which is always needed for electrophilic aromatic substitution reactions. It is going to react with a Lewis acid, AlCl3. Now this Cl is going to attach with chlorine with a pair of electron, and R positive is going to be generated as a strong electrophile. Now this carrying a positive charge and AlCl4 carrying a negative charge create some interactions just like this. Now since R positive is a strong electrophile, benzene is going to attack on this R group and a bond is going to form between this alkyl radical and benzene, and the other carbon will get a positive charge. Now just as in the other mechanisms that we have studied, this AlCl4 negative is going to abstract this proton, shifting the bond between carbon and hydrogen in the ring, restoring its aromatic character and giving you alkyl benzene. This H and Cl is going to make a bond giving HCl, and AlCl3, a neutral molecule, is going to be liberated. Since it is a catalyst, it is regenerated after the reaction. Students, here are some other examples of Friedel-Crafts alkylation. For example, if we are using methyl chloride, a methyl group is substituted on benzene giving you toluene. If we are using ethyl chloride, an ethyl group is substituted giving ethyl benzene. If you are using N-propyl chloride, so it is going to give you N-propyl benzene, and you can write the mechanisms just as we discussed. Now students, let us study Friedel-Crafts acylation. Introduction of acyl group R C double bond O in benzene by substituting hydrogen of the benzene ring in the presence of an acyl halide and a catalyst like aluminium chloride is called Friedel-Crafts acylation or simply acylation. Now you can see here is a benzene ring. This is an acyl chloride. Now in the presence of aluminium chloride, it is going to be converted into acyl benzene. An acyl group is substituted in place of hydrogen with the liberation of HCl. This is called Friedel-Crafts acylation. Students, since Friedel-Crafts acylation is also electrophilic aromatic substitution reaction, therefore we need to have a strong electrophile. Let us look into the detail of this mechanism. In the first step, you can see this is acyl halide. R C double bond O is acyl group. Along with Cl, it is called acyl chloride. Now students, it is going to react with aluminium chloride, which is a Lewis acid. Now this bond between carbon and chlorine is going to transfer to aluminium, making AlCl4 with a negative charge, leaving behind acylium ion. R C double bond O with a positive charge is called acylium ion. In the second step, benzene with its double bond acting as a nucleophile is going to attack on the acylium ion, the carbon of the acylium ion, and make a bond with it. The second carbon of this benzene will be deprived of the electron density and get a positive charge. In the next step, AlCl4 is going to abstract the proton, and the bond between carbon and hydrogen is going to restore the aromaticity of benzene ring. In this way, an acyl group is substituted in the place of hydrogen, and you can see AlCl3 is regenerated because it was used as a catalyst. This hydrogen with one Cl is going to combine to give you HCl. So this is the overall mechanism for Friedel-Crafts acylation. Students, the next topic that we have to study is the substituent effects. When an electrophilic substitution reaction takes place on a benzene ring, we get only one mono-substituted benzene because all the 6 positions in the ring are equivalent. Look at this chemical equation. We are having a benzene. Consider X as a substituent that have to be attached in place of hydrogen. Now students, to which carbon this X is going to attach? Since all the carbon atoms in benzene are equivalent, therefore this mono substituent can attach to any carbon because all of them are equivalent, and we are going to get mono substituted benzene. But students, when we have to synthesize a di-substituted benzene, the position of the second group into the ring depends upon the nature of the first group that we have already attached. The second substituent may enter at ortho, para or meta position. Now look at this general equation in which you can see that there was no problem for the substitution of the first group, which was making a mono-substituted benzene. But when we want to substitute the second incoming group, for example, if we consider it as Y, it can be substituted at ortho position, at meta position, or on the para position to make a di-substituted benzene. Now students, on chance basis, 40% ortho, 40% meta and 20% para di-substituted products are expected. However, the results do not agree with the chance substitution ratio that has been provided. For example, meta-nitrochlorobenzene is a main product of the following halogenation. Now students, the generalization is made that 40% ortho substitution might occur because we have 2 ortho positions in benzene, 20% for one, 20% for the second carbon. Similarly, 40% meta because we are again having 2 meta positions in the benzene ring. So chance of 20% substitution on this meta position and 20% on the other meta position. Since we are having only one para position in the benzene ring, therefore the chances is 20%. Now students, when an experiment was made for meta-nitrochlorobenzene, the main product was not according to this ratio. You can see a mixture of ortho-nitrochlorobenzene and para-nitrochlorobenzene is obtained from nitration of chlorobenzene. And you cannot see any substitution on the meta position. Students, this reaction brings us to a conclusion that it means that the groups already present on the benzene ring directs the second entrant, means the incoming group, and thus determines the position to which the second incoming group will attach. There are 2 types of such groups. The first one is ortho and para directing. Those groups which direct the incoming second substituent at ortho position also direct them to the para position. The second type of directing groups are meta-directing groups, that they are going to direct the incoming group to attach to the meta position. Now students, what are ortho-para directing groups? These groups release the electrons towards the benzene ring. We are going to discuss how by the resonance structures at ortho and para positions, because these positions are richer in electron for the attack of an electrophile. We are going to discuss it through the chemical reactions. The second incoming group is substituted at ortho and para positions. They also enhance the reactivity of the benzene ring. Means ortho para directing groups is going to enhance the reactivity of the benzene ring. Why? Because as we have already mentioned that the ortho and para position becomes richer in electron density. The second type of directing groups are meta-directing groups. Now students, these groups withdraw the electrons of the benzene ring, means it is opposite to ortho-para directing groups. Ortho-para directing groups increase the electron density towards the ring, whereas meta-directing groups withdraw the electrons of the benzene ring from ortho and para positions due to the electron withdrawing effect of such substituents. Means meta-directing groups are electron withdrawing. They are going to withdraw electron density towards themselves away from the benzene ring. The ortho and para positions are more electron deficient in this case. Remember that in ortho-para directing groups, these positions become enriched in electron density. But in meta-directing group, these position becomes electron deficient as compared to the meta position. Thus, the incoming electrophile will prefer to attack on the meta position rather than ortho-para positions. These groups are called meta-directing groups, and these groups decrease the chemical reactivity of benzene ring. Now students, let us study some rules on the basis of which we assign some groups as ortho-para directors and others as meta-directing groups. Now students, here are the rules for ortho-para directing groups. If the electronegativity of atom of the group attached to the benzene ring is greater than any atom of the group. Students, consider phenol as an example. This is the benzene ring. The group that is attached is OH. Now, if the electronegativity of the atom means that atom which is directly attached to the carbon of the benzene ring, its electronegativity is greater. If the electronegativity of the atom that is directly attached to the benzene ring is greater than any other atom or group of atoms that will be attached to this atom now, the whole group will act as electron repelling, and they are going to repel all the electronic density towards the ring. And it is going to increase the reactivity of benzene and direct the second incoming group at ortho positions and at para positions. Why students? Because the electronegativity of the other attached group is less. Therefore, this first atom is going to pull all the electronic density towards the ring, and it is going to get into the conjugation of benzene ring, increasing the nucleophilic character of the benzene ring and enhancing its reactivity. As we have already discussed that ortho-para directing groups, they enrich the benzene ring at ortho and para positions by increasing the nucleophilic character. Other examples are NH2. You can see the electronegativity of nitrogen is greater than the other two groups are attached to nitrogen, that is hydrogen. Therefore, it is also an ortho-para directing. Similarly, students, chlorine. Now, chlorine has no other atom attached to it, and therefore it do not have the danger of pulling the electrons. Thus, it is electron repelling, means it is going to repel the electron density towards the benzene ring, and hence it is ortho-para directing group. Now students, let us study how the ortho-para directing groups direct the incoming groups at ortho and para positions specifically. Now students, these are the resonating hybrid structures of phenol. Now you can see OH is ortho-para directing. Why? Because the electronegativity of the atom that is directly attached to the ring is greater as compared to the other atoms. Now student, this lone pair is going to make a bond between oxygen and carbon, making a double bond. Since the oxygen is using its lone pair to make a bond and is making 3 bonds over here, it will get a positive charge. Now the valency of this carbon will increase from 4 to 5. Therefore, the pi bond will break and reside on the next carbon atom as in negative charge. Now students, this negative charge is going to circulate in the ring. How? This negative charge is going to make a bond between these two carbon atoms, making a double bond, increasing the valency of the second carbon atom. Therefore, the pi bond will break and reside on the other carbon atom as a negative charge. Now this negative charge is going to make a bond with the next two carbon atoms, breaking the second pi bond. This pi bond will reside on the carbon as a negative charge over here. Now this negative charge will make a pi bond between these two carbon atoms, and as a result the pi bond between carbon and oxygen is going to be broken down and reside on the oxygen as a lone pair. So students, this is the resonance or delocalization of pheno. Now observe that during this process of delocalization, the negative charge is brought at ortho position, para position, and again ortho position. That is why increasing the nucleophilic character of these three positions. Now whenever an electrophile is going to approach, it is going to get attached to these three positions because of the presence of OH group, which is going to increase the nucleophilic character at these three positions. Therefore, the incoming group will attach at these positions specifically. The other examples of ortho-para directing groups are NCH3 whole twice, NH3, OH, OCH3, Cl, Br and I. All these are ortho-para directing groups. Now students, let us study an example of ortho-para directing group. Here we are having a toluene. The CH3 attached to benzene ring is an ortho-para directing group. Why? As you can see, to this carbon atom, the directly attached atom is carbon, which is having a greater electronegativity as compared to these three hydrogen atoms. Therefore, it is ortho-para directing. If we are going to carry out nitration, means HNO3 in the presence of H2SO4, you know that these are the two reagents for nitration. At 30 to 40 degrees Celsius, you can see we are having ortho-nitrotoluene along with para-nitrotoluene along with water. Now students, if you are going to increase the temperature, means increase the reactivity of this reagent, you can see that another nitro group is attached to a ortho position. As you can see in the second product also, the substituent are attached at ortho and nitro position. If you are going to further heat it about 100 degrees Celsius, now you can see it is further going to nitrate again at ortho and para positions. Means you will not see NO2 group at meta position in any of these reactions. This is showing that CH3 is acting as ortho-para directing group. Now students, let us study the rules for meta-directing groups. If the electronegativity of such atom, which atom? Which is directly attached to the benzene ring, it is less, means the electronegativity of the directly attached atom is less as compared to the other atoms. As you can see in this example, the electronegativity of oxygen is greater as compared to nitrogen, which is directly attached to this ring. It will be under the constraint. Why? Because this oxygen which is attached to this nitrogen is going to pull the electronic density towards themselves because of being more electronegative. Therefore, this nitrogen will be under constraint and it is going to withdraw the electrons from the ring outside towards the ring and making it less reactive and directing the incoming groups to the meta positions. For example, NO2, nitrogen is having less electronegativity as compared to oxygen. Similarly, SO3H is also meta-directing. Why? Because the electronegativity of sulfur atom is less as compared to the other atoms which are attached to it, that is oxygen. That is why it is going to withdraw all the electronic density from the benzene ring towards themselves, therefore directing the incoming group towards the meta position. Now students, let us discuss how the meta-directing groups direct the second incoming group specifically at meta position. Now as we have already discussed that NO2 is meta-directing group, Why? Because nitrogen, which is directly attached to the ring, is having less electronegativity as compared to other atoms which are attached to it, that is oxygen. Oxygen, being more electron negative, is going to withdraw the electron density towards itself. Now students, look at the resonance hybrid structures of nitrobenzene. The pi bond between oxygen and nitrogen is going to break and reside on oxygen as a negative charge. Now students, to satisfy the valency of this carbon and nitrogen, this pi bond will break and make a bond between carbon and nitrogen, depriving this carbon of its electron density and getting a positive charge. Now students, the second pi bond over here is going to satisfy the valency of this positive charge by shifting this pi bond between these two carbon atoms. But as a result, the electron density of this carbon atom will decrease. So the positive charge will shift on this carbon atom because its valency is not satisfied. To satisfy the valency of this carbon atom, this pi bond will break and shift between these two carbon atoms. And the positive charge will be gained by this carbon atom now because it is electron deficient. The bond between carbon and nitrogen will break and reside between these two carbon atoms to satisfy the valency of this positively charged carbon atom. Now students, the negative charge over here is going to shift between oxygen and nitrogen, again making a double bond. So this is how the resonance is going to take place. But students, notice the positive charge. It is brought at ortho position, para position, again at ortho position. Means in meta-directing groups, it is going to resonate in such a way, it is going to decrease the electron density specifically at ortho and para positions. Means that the electron density of meta positions are greater as compared to ortho and para positions in this case because it is not getting positive charges. So as compared to ortho and para position, the nucleophilic character of meta is a little greater. Therefore, the incoming electrophile will specifically attach at these meta positions because in this case, these two positions will be electron rich. Students, let us take an example of meta-directing group through a chemical reaction. As we have discussed that NO2 is a meta-directing group. If we carry out nitration of nitrobenzene, then you can see the second NO2 group is attached at the meta position because the already present NO2 group is going to direct it specifically at meta position. Other examples of nitro group are cyanide, nitro group, carboxyl group, and aldehydic group because the atom which is directly attached to the benzene ring is less electronegative as the other carbon atoms in these groups. Students,